And bring it forward. Okay, thank you everybody for joining us. Sorry the advert went out quite late. That was all my fault for not advertising sooner. Sorry. So this is Jorg Ebbing. So he was my PhD supervisor. We worked on the, we'd say the Karoo Basin, but it ultimately just became a very big 3D model of like South Africa. And so we were using gravity data to satellite gravity data to try and understand the deeper structure of South Africa. So I went to several tangents along the line. So Jorg has been doing a lot of stuff to do with with polar science. And so he's going to give a bit of a brief overview to us. I told him to not make it too technical. Okay, I'll take it away. I think the lights stay on, or do they go off? Does anyone know?
You can turn it on.
I think there's a sensor.
Wait.
I hope in the room they switch off.
You can't wait. Or maybe it's one of those switches by yours. Or we'll just see where they in the room.
I think that we need to start with the
I'm going to get other switch.
Oh, sorry.
And then that has a different gravy.
What would that mean?
Yeah. Or turn them on. There we go. Look at that. Or get cozy.
Okay, welcome. I tried to find the mouse and the keyboard. Hi.
Everyone, please ensure you are muted. So yeah, if you click on participants, if there are any issues, you can come here and just mute everyone.
Yeah.
Cool. And do you know how to do the laser pointer? Or would you like a laser pointer with your hands?
No.
It's easy if you do here. Then
Do the online.
Yep.
Okay.
Good. Okay, welcome everybody. That's a little bit impromptu presentation. That's just by chance that I visit for 2 days here in the university. Yes, that's where we are going next. And the title was Polar Science, so I hope nobody's confused. It's a little bit of glimpse on what we have been doing in Antarctica and just giving you ideas how to enhance actually sub-ice geology of Antarctica, and I will try to explain a little bit why this is an issue and why it's actually important. The work, a lot of my students have been doing most of the work, so I have to mention Marine Rüsing, Didishat, and Peter, and Stephanie, and Max, the last 2 not students, but a lot of people involved in this. I start with the movie. That's actually a little bit giving you an idea where we're coming from. So what we did originally building a 3D large-scale temperature model of Antarctica. And it's similar to what we did in Stephanie's PhD thesis, just for the entire continent, roping in gravity data, seismological data, and trying to get a hold of crustal thickness, lithospheric thickness. So temperature model on a very large scale. And you see all the different layers. This is a bit of this advertisement movies that we do that with the European Space Agency. Giving an idea, so if you're not so familiar with Antarctica, we have the eastern part, they call it the crater. There's a rifted area to the other part. So it's 2 very distinct parts of Antarctica, one tectonic younger, one tectonic older, and they're separated by here. That's the trans-Antarctic mountain chain, one of the continent. So the idea why we're doing this, and what you can see here, is to get the idea about the interaction of the ice and the solid Earth. So we know the ice sheets are moving and have different dynamics. And the question is how much is controlled by the underlying geology. For example, there's a difference if there's sediments or bedrock at the base, so the gliding conditions are different, but also the heat flow coming from beneath changes how the ice sheet can move. And that's actually important in last year's climate change and so on. So we know that there are a lot of changes in both the polar regions, both in Arctic and Greenland. And this is a part here, it's called the Amundsen Sea embayment. There's a huge mass loss at occurring with something like 160 gigatons per year, which is one of the main contributing factor for sea level change from Antarctica. Still not very large, but it's coming from this region. And here we have ice thickness up to 3 kilometers. There's a lot of potential for losing more ice and then also affecting sea level and so on. So what we did, and this was give a little bit of background older model. That's now a heat flow model, which is based on this regional model and some machine learning, which I actually did after my last visit here in South Africa in 2019. We started doing this. And you see typical crater behavior. You have heat flow between the order of 50 to 55 milliwatt per square meter. And then here's the western part where we have larger heat flow. And you see the link to South Africa, India, and Australia, because we don't know really the geology under the ice, so we have to go in the other continents which are surrounding to get some information. Now, here's the model based on machine learning, we use global data and so on. I'm not going to explain to you how we did it, just to do a lot of statistics. In the end, you get some idea, prediction of the heat flow. The problem is that it's a very coarse resolution, 50 to 100 kilometer, and that's not good enough to really understand the dynamics of the ice sheet. So we need higher resolution to really pinpoint where are the driving mechanisms, the basal conditions. So we have to go one step further and stepping away from these super regional models to more localized models. And that's what I try to do a little bit later on. Now, okay, go to the next slide. So one of the problems is that the geology of Antarctica obviously is not really well known, and that's shown here. So all which is white and these pinkish areas, that's all just unknown area. So 10 doesn't mean we just know anything. Outcrops are limited to the coast, and for most of the continent we have no idea. So of course we can do some reconstructions and then use the adjacent continents to get some idea. But if you do an interpolation from here to here, that's kind of a few thousand kilometers. And you can think yourself, if you interpolate geology from here to Kenya or Cameroon, it's difficult to interpolate over such a amount. Sorry. Then, of course, you have nice geophysical data, magnetic data, and that's like one of the compilations we just used a different data set from Australia, Antarctica, South Africa, Southern Africa. And the idea is to use this and to use some linking and interpolation of the geology. And what you see here is actually this huge gap between the anomalies that you see over Southern Africa and Antarctica. And of course, one of the questions is this correct? So is there a shift in the level? There was some discussion, of course, there's a crater in South Africa, so it might be that some reworking and so on, or is it just a data artifact? There was also the other interpretation, and just if there's something that's happened in the processing, because in magnetic data, you have to be very careful with the long wavelengths. You normally measure on the scale of the survey, and then the longer the wavelengths get, the larger the scale, you need other information to get the level right. So the question is, was the level right between Southern Africa and Antarctica? If you look at this, it might indicate there is some major change. Again, the question is geology or just the data artifact or processing left over. So that's one slide with a few details, but I try to get it, keep it light. So we developed a new processing method, which is a combination of an equivalent source model, which is one of these things that you use nowadays, and a combination of spherical harmonics. So spherical harmonics is what we normally use for the satellite data, and the equivalent source is just a proxy mathematical approximation to get a nice processing tool. You can do a lot of this filtering that you can do with Fourier transformation. You can also do the spherical harmonics. So the model is just representative of the true magnetization, but actually it's a meaningless model. It's just a model for processing. So just you have a thin layer and then you distribute some sources. And the trick is that you can use the different sources and then regard them as a dipole and then calculate the spherical harmonics for each dipole and just stack them up. Just a neat maximum mathematical approximation, which is computationally quite demanding. So people haven't been doing this in the last 20 years just because it takes time. So calculate a model for this, you have to wait 1, 2, 3, 4 weeks. No, not exaggerated, maybe a week. But then you just want to do it once. You don't want to do it all the time. So that's why it's not a common processing tool. But actually, it's nice then to combine the satellite data and aeromagnetic data. Again, you have to do it once. And then if you do it for the 4 surveys, in a month, you're basically done with doing the reprocessing. If you do this, something changes, and actually it changes that the data for Southern Africa are changing quite a bit. And the reason for this is that there was a difference, I guess, how the data from Southern Africa have been stitched to data from Botswana and so on. And it seems like by the stitching process, somehow the South African data kind of lost their level and were a little bit lower than they belonged to. And then by the combination with the satellite data, we actually could lift them up, and then they're all consistent, meaning so Southern Africa is similar to Antarctica, which other people has postulated. Some geologists were not happy that there is suddenly not this nice difference and this cratonic reworking and so on. So it's a little bit more boring than before. We did expect this because also the satellite data, now showing here is the satellite data only, you see more broader wavelengths, that the levels are connecting quite nicely, that it's not so prominent for Antarctica, has to do with satellite data and polar regions. If you want more details about this, ask Steph for the paper. She's co-authored, can explain all the detail in more. Good. So we have been ensured that the data are consistent. And that actually should help us now to get some idea about the sub-ice geology. And okay, I can zoom in again, and then you can see here some of the Kapwal craton and some of the Grünerhauger craton. So you can nicely outline all the geological formations on Antarctica and South Africa. And that's kind of what we're aiming to do. But you see also, if you go further to the hinterland, that the correlation is not getting as good. And you have to do again some form of interpolation. Okay, another movie. I can drink while this is running, and that shows you just the reconstruction of the magnetic data. And I've shown you the results always before. And you see for India, for example, we just have satellite data, therefore a little bit more broad wavelengths. Good. And now again, the next step is actually now getting to the geological data, to the geology under the ice. That's the idea behind this. Now, there are different approaches you can do, and we started with something very simple and actually followed the terracing method that Gordon Cooper has been developing and publishing in 2002. He demonstrated for the Redeport crater. Actually, it's a nice example. So what his method doing is instead of terracing, you actually separate anomalies in different parts. You somehow enhance the regional features and you suppress the local features. And the link was that he used the shape index for the anomalies, and that's kind of a normalization. And again, it's the method developed here in the house. We asked Gordon for this. We did successfully applied it for Greenland and also did some tests for Antarctica. And this is just to give you an idea how this looks for different shape index. Now that's the Greenland example. You see the most important is the threshold value. And then depending on the threshold value, you get different enhancements. That's the original magnetic anomaly. That's the different interpolations of interpolations. Now I'm not going to speak about Greenland, not to confuse you complete. But we also did it for Antarctica, and then you get these nice pictures for the gravity magnetics. And now you can actually, well, you can see some elements. We have the Transantarctic Mountain I spoke about here. That's the craton in the east. You see that this is the boundary with the Wilkes Land, and I can go one slide further because there are also some elements on this. And basically, you have three, but maybe not so good. There's three cratonic blocks, one here, the second one lying here, and the third one in here. And you have to trust me if you don't see it. That's basically, then you have the Western Arctic Rift Zone and you have the Arctic Peninsula. Now, you can judge yourself if this is a suitable picture to enhance or to link some geology from Antarctica or from Australia under the Arctic ice shield. The most important is that for the Australian part, which is lying here, it seems like some structures are continuing quite deep into the continent. For the South African part, it seems like they're more limited to the coastal areas. India might be relevant to look in again, as some of the structures might extend further to the Indians. For the magnetic data, you can do similar interpretation. So one would need a geologist which dares to put in some suture zones. And then they would look like this, and they're different applications. So this is we talk about the big Antarctic suture zone, which is connecting this line to this line, and of going through the entire continent. And I think that's the major suture zone, and others even doing interpretation. So you can find your geologist that you like best, and he will draw some lines for you. And then the question is how realistic this is. There's not really where we wanted to edit, so we go somewhere else as a geophysicist. We go for geophysical inversion and trying to connect this method with something which is in the subsurface. And that's the second slide with some information. So we did the joint inversion of gravity magnetics, which is called based on the variation of information. I don't explain the inversion equation, which is written here. Most important, just as a coupling term. What a coupling term means is that instead of it would be the parameter plot between gravity and magnetics or density to stability. You can have it in the joint inversion. If you don't do coupling, it's completely random, and we basically force it that the sources of the gravity and magnetic field should be similar. So that's our assumption that geology is both seen in the gravity and the magnetic field, that we have a similarity. But we don't say that's a one-to-one, it's a negative or positive correlation that the program can decide, but we also can decide that's not possible, that actually can say it doesn't fall into this. But we just would like to have the coupling. So we ask the program to find the coupling, and it doesn't find it, then we also can live with the results. Basically, that's what the program is doing. It looks for this variation of information. That would be the source of the gravity field, that's the source of the magnetic field, and we kind of ask the program to find solutions which are in this domain and not in the other parts. And if you do this, there's no coupling. And you see here, just a synthetic example. So it's going to be similar, and the same data as before for the coupling, then suddenly you see correlation between the sources. And what you can also see here, like this reddish anomalies, it can be both the blue or yellowish anomalies, so it's a negative or positive correlation. So we don't say another approach is where you have a linear relationship, but say this value of density belongs to this stability. Doesn't make sense for magnetics and gravity, so we just say there should be a geological similarity between the results. Good. And then you see, you get this kind of coupling terms with no coupling, kind of a big cloud of solutions, and with the coupling, we really get kind of a linear relationship, which we wouldn't accept a real example. It's a synthetic example. So a synthetic example works. For real example, that would be pretty surprising. Good. So we're going and concentrating now on Wilkes Land, this part of Antarctica. And that's the gravity magnetic data we used for the inversion. Most important is we use now the gravity residual of the regional model I showed you at the beginning. So we're not inverting the entire gravity, but just subtract the part which is correlated with near upper crustal sources. Magnetic data, they are limited in depth by the Curie isotherm, also sensitive to what is happening in the crust. We're assuming that we have two fields which can be correlated to each other. And okay, we had seen, and we can show that's the density and the susceptibility which you get from the inversion. And again, that's what you would do without the coupling. So that's the classic inversion. On this profile, not too much correlation. And if you see here, if you then force the correlation, you also in the density, the structure is getting far more visible, but also the stability is suddenly structures are appearing, which are otherwise smooth over because you don't force something. We go back and forth a little bit, so that's the advantage of the variation of information. But it's also nice is that normally in gravity and magnetics, you get these structures just extending from the surface to large depths. But if you cross the coupling, because gravity and magnetic have a different depth sensitivity, you suddenly see that there's also structures and dips and so on occurring back here, so you get more structural information. So that's actually quite important that we get to one step closer to geology. Still, you have to be careful. One has to be careful. That's still large-scale regional models. And currently, we're actually working at even one step further down to local scale, and then using more physics to really get a grip on this. But it's a nice way of coupling it. They're different. You can do different things like cross-gradient inversion, but this rich information is quite nice. It's also kind of a form of machine learning, and all students, my students, all want to do machine learning, so that's widespread, popular at the moment. Good. Now, getting this one step further, and that's looking at the Australia and the Africa combination. We're not the first to do this, and we look at the magnetic anomaly. We see some of the structures here in Australia nicely linking up to the suture here in Africa. And the gravity is not so visible, but you see the different cratons, Yana craton, Dora craton, and sorry, I forgot. And they're somehow lining up to the structures that we see on the Antarctic side. And if we do the inversion, also there, we suppress some of this shorter wavelengths anomaly, but for the long wavelengths. And these interpretations here have been done by Alan Aitken before, so we're not the first to do this. But clearly that the Australian geology links up with the geology in Africa. And again, we can interpolate this quite largely, quite far into the context. So that's quite nice. Now, it's a question, how much does it help us to understand? At the beginning, I was speaking about the geothermal heat flow. And now I show you the inversion results of susceptibility and density, and there's still some link to go back to the geothermal heat flow. Before we do this, just to get an idea of how good these results are. And so that's an inversion result. That's now, sorry, that's this profile here on the Australian side. And we have nice seismic data, and so it's very well constrained. And the model, of course, gives a perfect fit to the gravity and magnetic data you see above. We also can, from the model, predict some geothermal heat flow. I'll come back to this later. And here, the line drawings that you see here on the pictures, that's actually from the interpretation of the seismic profile. Now, you would say that it's not a complete 100 one-to-one correlation or an agreement, and I would say yes, but you have to be aware that's a super regional model. And then we just took this little profile here and compared how the super regional model looks to this one seismic profile. And for the scaling, it's actually surprising how well the line drawing is correlating with the results of the inversion. So we didn't expect that the fit was so good. We did so. You would normally think that you have to rescale the results again. But they look here, especially these vertical structures, which are nicely shown even in our inversion results. So that's kind of confirming that this method is quite promising, with all the caveats that you have to be careful, but also even the deeper structures. They're not perfectly fitted, but nicely seen in the inversion results. So there's a nice link between getting geology with this kind of inversion. Now, there's also heat flow on this value now. This profile now, the question is where the heat flow is coming from. And what we did, we used the petrophysical database, and then you can use the density and susceptibility and the measurements on the thermal conductivity to actually predict heat flow thermal properties to calculate heat flow values as well. And so what we did, we used the Australian database. We had all this information and then applied it to Antarctica and actually made a new prediction of the heat flow model for Antarctica. And that's the next. Well, that's first is the clustering analysis. So you have to do a little bit of, again, another form of machine learning, K-means clustering. So that's the cluster from the inversion, the density and susceptibility. And then you say that you would like to have certain distinct rock types that you do with the clustering. And then you can actually plot on top your rock properties and then actually point to the different parts, different thermal conductivities and so on. So it's a little bit of simplification with doing this with the clustering. So it means that all, which is here this grayish, that's the background, and all these different structures have now different heat production, radiogenic heat production, thermal properties. And then you can do the forward calculation of the heat flow model, and that looks like the lower one here. So that's now the new model. And what you see here, and again, we use the same machine learning approach that we used at the beginning. That's the old model. And now the new model actually has more details. And that's the kind of details that the ice sheet community is looking for. For example, this structure here, we also fit a little bit better the local heat flow values, the few that are available. So that's kind of the idea. By roping in more local information, you get a better fit to all the available information. For the machine learning, we actually limit ourselves only to 4 data sets in this case, just because we don't have other data sets which have this local information. For the first machine learning, we had done like 10, 12 data sets. Now with 4, that's very simple statistics that we did, but that suits the nicely. So the last step, which is missing, is that I should show you how this model is fitting the ice sheet better. I could have done this when my student was not on the boat for the last month in Antarctica, where she was doing the calculations and we just returned, I think yesterday from Antarctica, but she didn't send the results yet. But actually, she nicely demonstrated how the new heat flow model is fitting better the dynamics of the ice sheet. And there's one ice sheet here, which is fastly moving, and it seems to be at least related to this kind of elevated heat flow pattern that you see in this region. But there's certainly more work to do also along the entire margin of Antarctica to get a better grip on the geology. Good. It was just a short, brief overview, a little bit of glimpse what we're doing. I think the biggest advantage is really now this using this inversion approach for the gravity and magnetic data. The nice thing is that you can do it in a multi-scale approach. So we started with something which is really large scale, and now we're zooming into Wilkes Land, which is still, I think, the size of Southern Africa. And then we are already working on getting to the next level. And you can do this stepwise approach by improving the models and getting more and more to local geology, where we want to go. So therefore, next is the analysis on that near surface geology, which actually means that we are at the moment, we have been at the German Federal Institute measuring rock properties for Antarctica. I think 250 rock samples were just measured 3 weeks ago for density and susceptibility. For Greenland, we also measured thermal properties, so we try to establish a better rock geophysical database to get some better background to our models. And then, yeah, the idea is then to get a better proxy again for the ice sheet. Okay, thank you for your attention.
Thank you. I can't stand up for the picture. And thank you very much. Any questions? I asked earlier, why should we care so much about heat?
Well, in Antarctica, it's clear it's one of those key parameters controlling how the ice sheet behaves. It's kind of, it's a small role. Most of the melting is on the top, and that where the ice ocean interaction is. So that kind of 60–70%, and then the last third is actually of the ice sheet. So that's why it's important to really understand, quantify this. If you go for, like in Germany and so on, geothermal heat flow is important for geothermal energy. So that's actually a program that right now to remap the country to understand the geothermal energy, because alternative of green energies is getting more and more important. So now we had a program even to do geothermal assessment, but this was for the petroleum industry, but also even there to understand migration of hydrocarbons and so on. So everything is connected to heat. So that's quite important for our system.
There seems to be a dominant direction in some of the images. And is that at all related to the direction of flow of the ice? I mean, is the scouring out of U-shaped valleys at all apparent in the data, or is that too small scale?
I think it's too small scale. On the large scale, it's more like most people interpret it as the suture zones of tectonics and so on. That's you would see it if you go zoom into the nation scale. You see it in the bedrock topography, then you see kind of the valleys and so on, but not on the scale.
And then on the larger scale, you started off with that great movie showing the frontal thickness and the posterior thickness. How much influence is that having on the changes? Because it looked like there was a big step change.
Yeah, that's the most dominant source. It's kind of what we calculated with the residual. I think this is something like 30–40 milligauss at the end, which is left. The other 200 milligauss is coming from the regional model. So that's really dominating because you have the craton and then the rift zone. So it's a very long wavelength gravity signal. So what we did, we modeled the quantum-modified structure with the satellite gravity gradients, because they have this broad wavelengths, and then we just simulated against the gravity residual against the gravity data and used this for the second step of conversion. And then make sure to make the loop that the models are consistent with each other.
I really appreciate the re-leveling of the southern altitude data. That we've talked about that many times, and it needed doing certain things.
The coupling, no coupling. So the BT anomaly, which is supposed to continue instead of Antarctica, supposedly doesn't have a very strong gravity signal. So the coupling being helped, that you're forcing them to have a gravity, or even just forcing to have small density.
I guess you should try. You have the little space scale model. You can just use this to, and then try to see how you can enhance the structure. I guess there's probably a weak signal going to the BT, and that you should enhance with this. But I think that's a nice example actually to find it.
Jorg, you can see on this map, I think it's the aeromatic data for Australia and Antarctica. The holes in the data, the gaps in Antarctica, is that just the study, or are there any other reasons like accessibility or?
It's well, I have to say this one hole here that's filled by now, and the other part is actually more with inaccessibility. So that all the blanks are data which are not filled, but they have seen some measures from last year from the Chinese, the Indian, and so on. But well, it's just the distribution of stations around the coastal areas. So it's more like, I think this gap is a little bit more difficult because it's quite far away from the next station. And when you need somebody who's willing to fly there without the possibility to find a second landing site. Chinese are a little bit more risky than most European. Yeah, but this will be piece by piece. So that's big initiatives. There's also the called Rings project, which is now refly an entire Antarctic march to really understand the sub-ice bathymetry to really, it's also quite important because there's the most critical part of the ice sheets. It's the interaction of the ocean and the ice. So the melting kind of the oceans are sucking the ice into the ocean and then you have to understand really how the bathymetry is and how the changes are there. So there's huge efforts on Africa from a lot of countries. So the Chinese and Indians, there's always this idea that they may be also looking for mineral resources on the long run. On the long run, we don't know.
I know that one of the big things in Antarctica is find meteorites. And meteorites clearly the places where deflation occurs on the
yeah,
been controlled by some cases of photography. So this work we did science of, because usually in places where there are new ice leakage, detect satellites, but in this big areas that there might be concentration or even higher concentration of meteorites where things that we control at some certain photography that may be covered by sort of indicate areas.
It's I haven't looked at it. The only meteorite I was discussing, this is one, this Wilkesland crater, which is kind of like this. It's 1,000 kilometer crater, which has been proposed like 20 years ago. There were 2 or 3 papers on EGU abstract, and then it's completely it was again from literature, just on the Wikipedia page is still there as the potential Wilkesland impact crater. So that doesn't exist, I'm pretty sure. The smaller part, there are some uses, but it's different. I'm just zooming in, so the scale was so large at the moment.
Do the different ice fields, like the blue ice fields, have different densities? Is that?
Yes, there's different densities, but from my side, no. It's just it's 1 or 1 point. Yeah, they have different densities, but it's in the our densities. What do you actually?
It's usually resolvable within gravity.
Yes, if you have high resolution gravity, yes. But you have to think you have 3 kilometers of ice, and then if you have a density of 0.97 or 0.96 and so on, and that's kind of it's more the thickness which is more important. And the question is how good you can know the base. What we're trying at the moment is actually getting because with radar data, you can also estimate the temperature of the ice and trying to link these temperature profiles with our models. Because geothermal heat flow from these should be consistent, it isn't at the moment, and that's the way to combining more stuff, even more stuff, getting temperature from this. So all the codes and data are really. I just gave that the papers explaining the codes.
I mean, which papers did you get?
That's from my student. It's just the papers with the codes. The data are the. It's,
Are there links in the paper?
yeah. Otherwise, ask me to. So, like this in the environmental database for Africa, you can download the 16 gigabytes. So I don't. But you get all the background data from Africa, from most of the countries. Some of the countries don't. But yeah, it's a very exhaustive database.
Any other questions? If not, thank you everyone for coming. Thank you all for the talk. Take a drink on the way, and from the start of tomorrow morning. And if you miss any geotalks, look for them on the YouTube site. And this talk will be up in a few days.
Good. I stopped sharing and. No. I just end the meeting.